Hey guys, it's Natalie Vargas, and today we're going to be talking about topic 6.3, applications of differential calculus. Calculus in politics. Did you know that Joe Biden once referenced calculus in one of his speeches at the College of Worcester in 2008? He says, and I quote, "Well, in American history there have been about 5 or 4 points of inflection. Today we will learn about these points of inflection and what they mean." Before we begin, it is important that we define specific mathematical terms. The first derivative is the rate of change of the function. It is notated by f prime of x, dy over dx, or y prime. The second derivative is the rate of change of the rate of change of the function. These are its notations. Any of these can represent the second derivative. The sign of the second derivative also tells us the concavity of the curve. Let's take a closer look at what this means. For instance, a positive second derivative means the function will be concave down. If the gradient is decreasing, here we can see it's going from a positive then to a negative. The curve of the original function is concave down. Therefore, whenever the second derivative is positive, the concavity of the curve will be concave down. Now let's look at a negative second derivative. Whenever you have a negative second derivative, the function will be concave up. If the gradient is increasing, here we can see it's going from a negative to a positive. The curve of the function is concave up. Therefore, whenever the second derivative is negative, the curve of the curve will be concave up. It's also important that we know what stationary points are. Stationary points occur when the first derivative is equal to 0, and they are horizontal tangent lines. There are a couple types of stationary points. Whenever the second derivative is positive, your stationary points can either be a local minimum or a global minimum. These are represented on the graph below. Whenever the second derivative is a negative, you can either have a local maximum stationary point or a global maximum stationary point. These are also represented on the graph. Stationary points of inflection also occur when the first derivative is equal to 0. At the stationary points of inflection, the concavity of the curve changes. This means it can go from a positive to a negative or from a negative to a positive. Therefore, the sign of the second derivative changes at the stationary point of inflection. So now that we have the appropriate information, we're going to go ahead and solve our first example. Our first example says find the coordinates of the stationary points, and then we are given the equation of the curve f of x. F of x is equal to 2x cubed minus 1/2 x squared minus 12x plus 7. So our first step in this example would be to find the derivative of f of x. And in order to do so, you're going to use the formula in your formula booklet denoted as derivative of x to the n. And then once you multiply and subtract everything, you'll find that derivative of f of x is equal to 6x squared minus 6 minus 12. And your next step would be to set this equal to 0. And once you do so, you can start solving for x. In this case, it is a lot easier and more efficient to simply factor and then set each one of them equal to 0. Next, all you're going to do is solve for x. So first, on this side, you would subtract 4, and on this side, you would add 3. And then now you're going to divide by 3 on this side and divide by 2 on this side. And you'll find that x is equal to -4/3 and x is equal to 3/2. So now that you have your x coordinates, you want to find your y coordinates. And in order to do that, you're going to substitute your x coordinates into f of x, the original function of the curve. And when you substitute -4/3 for x, you're going to find that f of -4/3 is equal to 469/27. Next, you're going to do the same thing with the 3/2 and substitute it into your original function, f of x. And once you substitute 3/2 into x, you'll find that f of 3/2 is equal to -43/8. And so what we just found are our y coordinates. So now your final answer is -4/3, 469/27, and 3/2 with a y coordinate of -43/8. And these are your stationary points. And yeah, this concludes example 1. Now let's move on to the second example. In the second example, we are asked to not only find the coordinates, but also the nature of the stationary points of the curve y equals x to the 4th plus 2x to the 3rd minus 12x squared. And as we did in the previous example, our first step would also be to find the derivative of y. And you would also use the formula in your formula booklet. And once you multiply everything and subtract everything, you're going to find that the derivative of y is equal to 4x cubed plus 6x squared minus 24x. The next thing that you want to do is set it equal to 0. So now you can start solving for x. In this case, you notice that every number has an x. Therefore, it would be very smart to simply factor out the x. And once you do so, you'll be left with a binomial inside the parentheses. And now you can set each one of these equal to x, or to 0. So you'll find that x is equal to 0. But then you can also solve for the x in the binomial. And I used the formula, the quadratic formula, and the 4 is our A, the -6 is our B, and the -24 is our C. And I just substituted this into our quadratic formula. And then I simplified it, and you'll find that x is equal to -6 plus or minus the square root of 420/8. And you want to substitute this number into the original function y. And first, I'm doing the addition. So I'm doing -6 plus the square root of 420/8. And then I'm going to do the subtracting one. Notice that these signs are different, and it's important that you do both because they will give you different numbers. And then finally, also did it for 0. I substituted 0 for x. And once you do the math and you simply solve the equation, you'll find that these are your y coordinates. So these are your stationary points of inflection. -6 plus the square root of 420/8. And then the y coordinate is -16.7. And I did this equal to 3 significant figures for all of them. This is your x and this is your y. -6 minus square root of 420/8, and then the y coordinate is -84.0. And then finally, our last point of stationary point is x, y. So the second part of the example is asking us to find the nature of the stationary points. So what does this mean? This means to determine whether the stationary points are global maximums or global minimums, or local maximums or local minimums. So our first step would be to find the second derivative. And we already knew the first derivative and our stationary points. So we're going to use this information to find the nature of the stationary points. You would use your formula booklet to find the second derivative. and you'll find that the second derivative is equal to 12x squared plus 12x minus 24. And then what you want to do is take into consideration your your stationary points, and you're going to substitute your x coordinate into your second derivative, and you're going to substitute that for x, and then you're going to find that the second derivative is positive for -6 plus the square root of 420 over 8. Then you're going to do the same thing with your next x coordinate, and you're going to find that the second derivative is also positive for that coordinate. And you're going to do it with your last x coordinate, which is 0. And you're going to find that the second derivative in this case is actually equal to a negative. In this case, you can see that 37.1 is lower than 67.9. Therefore, this is a local minimum. Remember, whenever our second derivative is positive, we know that this can either be a local minimum or a global minimum. So then 67.9 is a lot higher than 37.1. Therefore, we know that this is a global minimum. And remember, whenever our second derivative is a positive value, we know it can either be a local or a global minimum. And then when we substituted 0, we found that the second derivative was equal to -24. And whenever the second derivative is equal to a negative value, it is a local maximum. So that's how you determine the nature of the stationary points. And you determine that this point is a local minimum, this point is a global minimum, and the final point 0, 0 is a local maximum. Now this is an example for you to do on your own. Find the coordinates and nature of the stationary points f of x equals 2x to the third plus 3x squared minus 12x plus 1. So first you're going to find your stationary points, and then you're going to determine if it's a global, local, minimum, or maximum. Go ahead and pause this video, and then the answers will come shortly. And these are your answers. The stationary points are -221 and 1, -6. -221 is a local maximum, and -1, -6 is a local minimum. The next example that you're going to do on your own, this one is simply asking you to find the coordinates of the stationary points. And go ahead and pause this video, and then the answers will come shortly. So these are the coordinates of your stationary points. -14 plus the square root of 376 over 30, and 14.7 is your y coordinate. And then make sure it is 3 significant figures. And then your second stationary point is -14 minus the square root of 376 and over 30, and your y coordinate is 20.1. And those are your answers. Thank you for watching.